welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 140, word break 2. This is a fascinating problem where we need to generate all possible sentences by breaking a string into valid words from a given dictionary. Let's dive in and break down the solution step by step. In this problem, you are given a string S and a dictionary of words called WordDict. Your task is to find all possible ways to segment S into sentences such that each word in the sentence is a valid word from WordDict. The order of the words in each sentence must follow the order of characters in S. For example, if a word starts at a certain position in the string, it must remain in that position in the resulting sentence. Now, an important detail here is that you can reuse words from WordDict as many times as necessary to form valid sentences. Additionally, the solution needs to return all possible sentences, not just the count of them. The input consists of two parts, S, which is a non-empty string made up of lowercase English letters, and WordDict, a list of lowercase English words. The output is a list of strings, where each string represents a valid sentence created from S using words from WordDict. Let's look at the first example. Here, the input string is S equals cat sand dog and the dictionary of words is WordDict equals cat, cats, and sand, dog. The output is a list with two sentences, cat sand dog, cats and dog. For the first sentence, cat sand dog, the string is segmented into the words cat, sand, and dog, each of which is present in the dictionary. Similarly, for the second sentence, cats and dog, the string is segmented into cats, and dog, all of which are also in the dictionary. Both sentences are valid because every word used is part of WordDict, and the order of the words follows the order of characters in S. Now, let's analyze the second example. Here, the input string is S equals apple and the dictionary is WordDict equals apple, pen, pine, pineapple. The output is a list of three sentences, pineapple, pineapple, pineapple. For the first sentence, the string is segmented into pine, apple, pen, and apple. For the second sentence, it's divided into pineapple, pen, and apple. Finally, the third sentence is formed by splitting the string into pine, apple pen, and apple. All three sentences are valid because every word used comes from the dictionary, and the sequence of words matches the sequence of characters in the original string. In the third example, the input string is S equals cat sand dog and the dictionary is WordDict equals cats, dog, sand, and cat. Here, the output is an empty list. This is because there is no valid way to segment the string cat sand dog using only words from the dictionary. For instance, while cats and dog are valid words, the substring ando cannot be formed using any combination of words from WordDict. Now, let's consider some constraints and edge cases. The string S will always have a length between 1 and 20, while the dictionary can contain up to 1,000 words. The total length of all dictionary words combined will not exceed 10,000 characters. Also, every string, whether S or words in the dictionary, will only consist of lowercase English letters, and all words in the dictionary are guaranteed to be unique. Finally, edge cases include scenarios where no valid sentences can be formed, where the entire string matches a single word in the dictionary, and where overlapping or repeated words need to be handled correctly. To approach problem number 140, word break 2, we need to generate all possible sentences by segmenting the input string S into valid words from the dictionary WordDict. This challenge combines string segmentation with backtracking, making it both intricate and rewarding to solve. First, let's discuss the brute force approach. The intuition here is simple. For each index in the string, we attempt to match every possible substring with a word in WordDict. If a match is found, we recursively solve the remaining portion of the string. During this process, we use backtracking to explore all possible segmentations, appending valid words to the current path, and saving the constructed sentence once the end of the string is reached. However, this approach is computationally expensive, with a worst-case complexity of O(2 to the power of n), as we are redundantly solving the same subproblems multiple times. This makes it impractical for larger inputs. To address this inefficiency, we can introduce memoization to optimize the backtracking process. By storing results of already computed substrings, we can avoid recalculating solutions, significantly reducing redundant work. With backtracking and memoization, the process becomes more efficient. If a substring Si has already been evaluated, we can simply return the result from the memo dictionary instead of recomputing it. Otherwise, we perform backtracking as before, but store the results in memo once computed. This optimization drastically reduces redundant evaluations, improving performance. The time complexity improves to O(n) squared for substring evaluations combined with O(2 to the power of n) for generating all combinations, which is much faster in practice than the brute force approach. That said, there is a trade-off. While memoization reduces computation time, it requires additional memory to store intermediate results. Another alternative is to use dynamic programming with tabulation. In this approach, we iteratively compute all possible sentences for smaller substrings and use them to construct results for larger substrings. For this, we define dpi as the list of sentences formed from S0i. For each index I, we check all possible substrings S(j)i and combine valid results from dp(j) with S(j)i. While this has a complexity of O(n) cubed, due to nested loops and string concatenation, managing intermediate sentence combinations can become cumbersome and less intuitive compared to backtracking. Given the options, backtracking with memoization is the most efficient and practical solution for this problem. The key insight here is recognizing the overlapping subproblem structure, which makes memoization a perfect fit. Backtracking also allows us to directly construct valid sentences without the need to manage complex intermediate states, as is required in dynamic programming. By leveraging a dictionary to store pre-computed results, we avoid recalculating solutions for the same substrings, significantly improving the runtime. This approach strikes a balance between time complexity and ease of implementation. Compared to brute force, it eliminates redundancy, making it feasible for larger inputs. Compared to dynamic programming, it offers a more intuitive top-down approach for constructing sentences dynamically. While memoized backtracking does require additional memory for storing results, the performance improvement is a reasonable trade-off, especially when solving this type of problem. By using backtracking with memoization, we achieve an efficient solution that balances clarity, reusability, and scalability. This approach not only simplifies the logic but also ensures that the solution can handle larger inputs effectively. By avoiding redundant computations and directly constructing valid sentences, it offers a powerful and elegant way to solve the problem. This makes memoized backtracking a natural choice for tackling the challenges presented by WordBreak 2. The problem, WordBreak 2, challenges us to generate all possible sentences by breaking down the string S into valid words from a given dictionary, WordDict. Each word in the dictionary can be reused multiple times, but we need to ensure that the entire string is segmented into meaningful words in their original order. To solve this, we can use a backtracking approach combined with memoization for efficiency. The first step is to pre-process the dictionary by converting WordDict into a set. This allows for O(1) lookup time, making it much faster to check if a substring is valid. Next, we define a recursive backtracking function called dfs start, which will return all possible sentences starting from the given index start. For the base case, if start equals the length of the string, we return an empty list, as there are no more characters to process. To enhance performance, we employ memoization by using a dictionary memo to store results for previously computed starting indices. If a starting index has already been processed, we simply retrieve and return the result from memo instead of recomputing it. To explore all possible segmentations, we iterate over potential end indices, ranging from start +1 to the length of the string +1. For each end, we extract the substring S, start end, and check if it exists in the dictionary. If it's a valid word, we proceed by recursively calling dfs end to solve for the remainder of the string. The results of this recursive call will give us all possible sentences for the remaining portion of the string. Then, we combine the current word with each sentence generated from the recursive call, ensuring proper spacing between words, and store these results. Once all valid segmentations are processed for a starting index, we store the results in memo to avoid redundant computations in the future. This ensures that every starting index is computed only once, significantly improving the algorithm's efficiency. The key insight here is that backtracking, when paired with memoization, prevents repetitive computations for overlapping subproblems, which would otherwise lead to exponential time complexity. Memoization is a critical optimization here because it ensures that each starting index is only processed once, dramatically reducing redundant calculations. Without memoization, the algorithm would repeatedly recompute results for the same substrings, leading to inefficiency. Another important detail is substring validation. By converting word-dict into a set, we achieve O(1) lookup time for checking whether a substring is valid. This pre-processing step is crucial for keeping the algorithm fast. It's also important to handle edge cases, such as when the dictionary is empty or when the input string S is empty. In both scenarios, no valid segmentations can be formed, so we return an empty list. The data structures used in this algorithm include a set for efficient substring validation, a dictionary for memoization to store intermediate results, and a list to collect sentences during the backtracking process. For complexity, the time complexity depends on the length of the string and the number of valid sentences generated. Each starting index explores up to n substrings, and memoization ensures that this is done only once per index, leading to a time complexity of O(n)² plus k, where k is the total number of valid sentences. In terms of space complexity, the algorithm requires space for memoization, which is proportional to the length of the string, O(n). Additionally, the recursive call stack can go as deep as the length of the string in the worst case, contributing another O(n). Combined, the total space complexity is O(n) plus k, where k is the space required to store the final list of sentences. Now, let's look at the pseudocode. First, we pre-process the dictionary by converting it into a set for efficient lookups. We also initialize an empty dictionary memo to store results for subproblems. The recursive function dfs start begins by checking if start equals the length of the string, in which case it returns a list containing an empty string, representing the base case. If the value for start has already been computed and stored in memo, we return the pre-computed result. Otherwise, we initialize an empty list, sentences, to store valid sentences starting from the current index. We then iterate through possible end indices, extract substrings, and check their validity in the dictionary. If a substring is valid, we make a recursive call to compute sentences for the remaining portion of the string. For each valid substring, we combine it with the results returned by the recursive call. If the recursive call returns non-empty sentences, we append the current word followed by a space and the subsequent sentence to the results. If no subsequent sentence exists, we simply append the current word. Once all possible segmentations are processed for the current starting index, we store the resulting sentences in memo to ensure we don't recompute them later. Finally, we return the stored results. After defining the function, we initiate the process by calling dfs0, which computes all valid sentences starting from the beginning of the string. The results are stored in the variable result, which contains all possible segmentations of the string S into valid words from word-dict. This approach ensures that we generate the required sentences efficiently while avoiding unnecessary recomputations, thanks to memoization. This Python implementation solves LeetCode problem number 140, word break 2, using a backtracking approach with memoization. The goal is to generate all possible sentences by segmenting the input string S into valid words from the dictionary word-dict. ###explanation. 1. Initialization. The word break function begins by defining an inner backtrack function, which takes the current start index as an argument. This function recursively explores all possible segmentations of the string starting from the start index. 2. Base case. If start equals the length of the string S, it means we have successfully segmented the entire string. In this case, the function returns a list containing an empty string, which serves as the base case for constructing sentences. 3. Memoization check. Before performing any computation, the function checks if the result for the current start index is already stored in the memo dictionary. If so, it directly returns the pre-computed result to avoid redundant work. 4. Main logic. The function iterates through all possible end indices, end, from start plus 1 to len, s, plus 1. For each end, it extracts the substring word equals s, starting end, and checks whether this word exists in the word set, a set of words derived from word-dict for faster lookups. 5. Recursive calls. If the substring word is valid, the function makes a recursive call to backtrack, end, to find all valid sentences for the remaining portion of the string. For each valid sentence returned, it concatenates word with the rest of the sentence and adds it to the sentences list. 6 is memoization. After computing all possible sentences for a given start, the function stores the result in the memo dictionary to ensure that subsequent calls with the same start index are efficient. 7. Return result. Finally, the word break function calls backtrack 0 to initiate the process from the start of the string and returns the list of all valid sentences. ### complexity analysis. Time complexity. The algorithm explores all possible segmentations of the string, with memoization ensuring that each substring is processed only once. The complexity is exponential in the worst case but is significantly reduced by memoization. Space complexity. The space complexity is determined by the recursive call stack and the memoization dictionary, making it proportional to the length of the string. This implementation is optimized for performance and handles edge cases such as an empty string or an empty dictionary effectively. Here, we begin the Java implementation of the word break 2 problem. First, we create a solution class with a method wordBreak that takes in the input string s and a list of words, wordDict. To optimize lookups, we convert wordDict into a hash set called wordSet. This allows us to efficiently check for the presence of words during processing. Next, we define a hash map named memo, which will be used for memoization. This helps us avoid redundant computations by storing results for already processed indices. The core of our solution lies in the backtrack method, which performs a recursive depth-first search. It starts by checking if the current start index has already been computed and, if so, retrieves the result directly from the memo. If the start index equals the length of the string, it means we've successfully processed the entire string, so we return a base case result of a list containing an empty string. We then initialize an empty list, sentences, to store all possible sentences formed from this index onward. The for loop iterates over possible end indices, creating substrings from start to end. If the substring is a valid word in wordSet, we recursively call backtrack with the updated end index to find sentences formed from this point onward. The recursive call returns a list of possible sentences for the rest of the string, which we iterate over to construct complete sentences. For each sentence in the return list, we concatenate the valid word we just found with the sentence, adding a space if the sentence is not empty. Once all valid combinations for the current start index are explored, we store the resulting list of sentences in the memo map to avoid recomputation in future calls. Finally, we return the sentences list, which contains all valid sentence combinations that can be formed starting from this index. This approach ensures that we efficiently explore all possibilities while leveraging memoization to reduce redundant computations, making the solution both elegant and performant. We begin solving the problem with an example where the input string is cat sandog and the dictionary contains the words cat, cats, and sand, and dog. First, we convert the word dictionary into a set for faster lookups, resulting in wordSet equals cat, cats, and sand, dog. Next, we initialize an empty memoization dictionary, memo equals. This will help us store intermediate results to avoid redundant calculations. We then start the recursive backtracking process from index 0 of the string. At each step, we try every possible substring starting from the current index and extending to the end of the string. For example, we check the substring cat, which spans indices 0 to 3. Since cat is in wordSet, we recursively call the backtrack function starting at index 3 to solve for the remaining portion of the string. Moving forward, we then explore the substring sand, which spans indices 3 to 7. As sand is also in the wordSet, we recursively call backtrack starting at index 7 to solve for the remainder of the string from there. At index 7, we now explore the substring dog, which spans indices 7 to 10. Since dog is in the wordSet, we recursively call backtrack starting at index 10. Here, the index equals the length of the string, so we return an empty string as the base case result. Once we have this base case, we start building the results backward. From the backtrack call at index 7, we combine the substring dog with the base case result, forming dog. We then memoize this result as memo 7 equals dog. Next, from the backtrack call at index 3, we combine sand with the result dog, forming sanddog, and memoize it as memo 3 equals sanddog. Finally, from the initial backtrack call at index 0, we combine cat with sanddog, forming cat sand dog, and memoize it as memo 0 equals cat sand dog. The final output for this example is the single valid sentence, cat sand dog. Now, let's look at another example where the input string is apple and the dictionary contains the words apple pen, pine, and pineapple. As before, we start by converting the word dictionary into a set, resulting in word set equals apple, pen, pine, pineapple, and we initialize an empty memoization dictionary, memo equals. The backtracking process begins at index 0, and we try various substrings starting from there. For instance, the substring pine, which spans indices 0 to 4, is found in the word set, so we recursively call backtrack starting at index 4 to process the remainder of the string. Continuing, we explore the substring apple pen, which spans indices 4 to 12. Since apple pen is also in the word set, we make another recursive call to backtrack starting at index 12 to solve for the rest of the string. At index 12, we now examine the substring apple, which spans indices 12 to 17. This substring is in the word set, so we recursively call backtrack starting at index 17. Since 17 equals the length of the string, we hit the base case and return an empty string as the result. We then build the solution by combining results backward. From the backtrack call at index 12, we combine apple with the base case result, forming apple, and memoize it as memo 12 equals apple. From the backtrack call at index 4, we combine apple pen with apple, forming apple pen apple, and memoize it as memo 4 equals apple pen apple. Finally, from the initial backtrack call at index 0, we combine pine with apple pen apple, forming pineapple pen apple, and memoize it as memo 0 equals pineapple pen apple. The final output for this example is pineapple pen apple. In the third example, the input string is cat sand dog, and the dictionary contains the words cats, dog, sand, and cat. We begin by converting the word dictionary into a set, resulting in word set equals cats, dog, sand, and cat, and we initialize an empty memoization dictionary, memo equals. As we attempt to segment the string using recursive backtracking, we explore various substrings like cats, cat, and others. However, no valid combination of words from the dictionary can fully cover the input string. For example, after processing valid substrings like cats or cat, we reach portions of the string that cannot be matched with any word from the dictionary. As we backtrack, we memoize these intermediate invalid states to avoid redundant calculations. Ultimately, since no valid segmentation is found, the result for this input is an empty list. The time complexity of our solution is influenced by the recursive backtracking and memoization process. First, let's consider the recursive calls. The backtrack function is invoked for every possible starting index in the string S, and there are n such indices where n is the length of the string. For each starting index, the function iterates through all potential ending indices to extract substrings. This inner loop can run up to n start times, leading to O n squared substring checks in the worst case when you sum this across all recursive calls. Additionally, for each substring, we check if it exists in the word set, which is an O1 operation because the hash set provides constant time lookups. Next, memoization plays a critical role in optimizing the solution. The memoization dictionary ensures that each starting index is processed only once, preventing redundant computations. Without memoization, the algorithm could end up exploring all possible combinations of substrings, which would result in exponential time complexity. Another aspect to consider is sentence formation. Once valid substrings are identified, the algorithm generates combinations of sentences by concatenating results from recursive calls. The time required for string concatenation depends on the number of valid sentences and their average length. If the number of valid sentences grows exponentially, this adds an O2 to the power of n factor to the overall complexity. Combining these aspects, the worst-case time complexity becomes O n squared plus 2 to the power of n, where O n squared accounts for substring checks and O2 to the power of n accounts for generating all valid sentences. The space complexity of the solution arises from three main components. First, the memoization dictionary stores results for each starting index. In the worst case, the dictionary could hold entries for all n indices, with each entry potentially storing up to O2 to the power of n sentences. This means the memo dictionary alone could take exponential space. Second, the recursive call stack contributes to the space usage. The maximum depth of the recursion is proportional to the length of the string, resulting in O(n) space usage for the call stack. Finally, the word set used to store the dictionary words requires O(m) space, where m is the number of words in the dictionary. Combining these factors, the overall space complexity is O(n plus 2 to the power of n plus m. Analyzing different scenarios, we see that the complexity varies depending on the input. In the best case, if the string s cannot be segmented into valid words, the recursion terminates quickly, and the complexity is dominated by substring checks, which take O(n squared). In the average case, the complexity depends on the number of valid words and their combinations. It typically falls between O(n squared and O(2 to the power of n). The worst case occurs when all substrings of s are valid words, leading to O(n squared plus 2 to the power of n, due to exponential sentence generation. Comparing this solution to a brute force approach, which generates all possible splits of the string and checks each one, the brute force method would have a time complexity of O(2 to the power of n asterisk k, where k is the time to check each split. By leveraging memoization and efficient lookups, our solution optimizes this to O(n squared plus 2 to the power of n, making it more optimal for this problem. To understand the mathematical justification behind the complexity, the O(n squared factor comes from iterating over all possible substrings in the string. This involves nested loops for every starting and ending index. The O(2 to the power of n factor arises from the exponential number of ways to form valid sentences, as each substring can either be included or excluded in the final result. Memoization ensures that we only process each starting index once, which prevents redundant computations and contributes to the efficiency of the solution. However, the space complexity grows with the number of valid sentences stored in the memo dictionary, which can be as high as O(2 to the power of n in the worst case. These factors combined explain the overall time and space complexity of the solution. One common mistake when solving word break 2 is not memoizing intermediate results during backtracking. Without memoization, the algorithm can end up recalculating solutions for overlapping subproblems repeatedly, which leads to exponential time complexity. This inefficiency can drastically slow down the solution and may even result in time limit exceeded errors. Another pitfall is ignoring edge cases. For example, the input string could be empty, or the dictionary itself might be empty. Additionally, there could be scenarios where the words in the dictionary do not cover the entire string, making segmentation impossible, or the dictionary might contain repeated words. If these cases are not handled properly, the solution could produce incorrect results or runtime errors. Lastly, using a list instead of a set for the dictionary is another frequent oversight. Since list lookups take k time, where k is the number of words in the dictionary, this can significantly slow down the algorithm. By contrast, using a set reduces the lookup time to O(1), making the solution more efficient. Another mistake to watch out for is implementing an incorrect base case in backtracking. It's important to return the correct result when the string is fully segmented, otherwise, you risk making invalid recursive calls, which can lead to incorrect outputs or even infinite recursion. Additionally, some may confuse word break 2 with word break I. While word break I only checks if segmentation is possible, giving a Boolean result, word break 2 requires generating all valid segmentations, which is a much more complex task. Reusing the logic from word break I without proper modifications won't work. From an interview perspective, the optimal approach combines backtracking with memoization to efficiently explore the solution space. This problem highlights a recurring pattern in algorithmic problem solving, where recursion with memoization, also known as top-down dynamic programming, or iterative dynamic programming, known as bottom-up, is key. Be ready to explain why you chose backtracking over iterative DP, and discuss the time and space complexity trade-offs. If you find the problem challenging, a useful strategy is to first solve word break I to determine if segmentation is possible. Then, you can extend the solution to generate all valid sentences. Finally, make sure to explicitly discuss edge cases during interviews, such as empty strings or dictionaries. This shows your ability to think critically and handle corner cases effectively. This problem is closely related to several others on LeetCode. For instance, word break, which is problem number 139, asks whether the string can be segmented into a sequence of dictionary words, providing a simpler foundation for solving word break 2. Another related problem is concatenated words, problem number 472, where the goal is to find all words in a list that can be formed by concatenating other words from the same list. Palindrome partitioning, problem number 131, is another example, as it involves generating all possible ways to partition a string, but this time ensuring each substring is a palindrome. Finally, restore IP addresses, problem number 93, is a similar combinatorial problem where you generate all valid IP addresses by inserting dots into a string. Exploring these related problems can help you develop a deeper understanding of recursion, backtracking, and dynamic programming principles. When approaching word break 2, it's worth considering alternative methods beyond backtracking with memoization. One such approach is bottom-up dynamic programming, where you pre-compute valid segmentations and then construct the results. While this approach can use less stack space, it's often harder to implement and less intuitive when generating all combinations. Another option is a tree-based approach. By constructing a tree for the dictionary, you can guide the backtracking process more efficiently, pruning invalid paths early. However, building the tree involves higher pre-processing costs, which might not always be justified unless the dictionary is very large. Finally, breadth-first search, or BFS, can be used to iteratively explore all possible segmentations. With memoization, BFS can avoid redundant work, and since it doesn't rely on recursion, it eliminates the risk of stack overflow. However, BFS may require additional memory to manage the queue. Each of these approaches has its trade-offs, so the choice depends on the specific constraints and requirements of the problem. Great job making it to the end. In this session, we tackled word break 2 using a combination of backtracking and memoization. We highlighted the importance of recursion and dynamic programming for solving these types of problems. Don't forget to keep practicing and applying these concepts to similar problems. Thanks for watching, and we'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!